Hello and welcome to lesson 40, where today we are looking at the applications of the dot product. So we did see the dot product last lesson, and we worked with a lot of the properties, both for geometric and algebraic vectors. And now we're going to see some applications of why the dot product is useful to us. So specifically, we're going to be looking at scalar and vector projection, as well as applications in real life, including work and power. So starting with scalar projection of a vector of A on vector B. So if we have two vectors and vector A is defined as OA and vector B is defined as OB, and these are placed tail to tail, and theta is the angle between them with theta between 0 and 180 degrees inclusive, then the scalar projection of A onto B is given as OP, and this is the magnitude of vector A times cosine of theta. So what this means is, so here's vector OB in all of them, and then we have vector A. And I've given you the three different cases. So when theta is between 0 and 90 degrees inclusive, or sorry, not inclusive. This should be not inclusive here because I'm going to show you what it looks like for theta is equal to 90 degrees. And this one is between 90 degrees and 180 degrees, inclusive of the 180 degrees. So what this means is when we are projecting vector A onto vector B, we draw the perpendicular line from the endpoint A onto vector OB. And where we land, that magnitude there is given by, and this is vector A. Then this magnitude is the scalar projection of vector A onto vector B, and it has magnitude A times cosine of theta, where theta again is that angle between them. Now, what this is doing is, again, just drawing that perpendicular line and determining the magnitude of the line formed from point O, which was their common tail, and point onto vector B wherever it's intersecting with this line. So again, this is a right angle. Now, in the case where theta is between 90 degrees and 180 degrees, you could see that this is now being going past where vector OB is. So really what you do is we find that same perpendicular line, but now we have to extend vector OB in the opposite direction, and this is now our new value, which is going in the opposite direction to OB. And this is just because the way the angle is, we're not lined up with vector OB the same way we saw in this case. And our last case is when theta is 90 degrees, so we have a right angle, and these two are perpendicular. So then we know that cosine of theta is just 0. So in this case, we don't have a projection here. Now, notice here, I was specifically saying scalar projection of A onto B. The reason for that is with scalar projection, it does matter which vector you're projecting onto the other. I'm sure you can see if we were doing a projection of vector B onto A, this would now be the line we consider, which is the perpendicular here. And then we would be looking at this not very accurate, but there we go. So we were looking at this red magnitude over here, which is clearly different from the other magnitude. And so to give it a definition of how we calculate it, the scalar projection of A onto B is given by the dot product A and B and divided by the magnitude of B. And this will also, sometimes you may see it written in this notation, and this is the projection of A onto B. This one should be now B onto A. And so, yeah, so projection of B onto A, remember, dot product is commutative, so this would be B dot product A, but again, it doesn't matter, it's the same dot product. And now we're dividing by the magnitude of A. And this can also be written as projection of B onto A. And this is what that would look like visually as a difference. And you can see these two quantities are different if we're projecting A onto B versus if we are projecting B onto A. And this is that notation that I was just mentioning. Now, with scalar projection, we have two key ideas. So the scalar projection of A onto B is not necessarily equal to scalar projection of B onto A. It could be, but it's not necessarily equal. And the scalar projection of A onto B is independent of the length of B. So as we were seeing up here, it didn't matter what the length of B is. If this is extended here or if this is shorter here, you are still, you have to extend OB or see it visually as extended in both directions in order to determine that scalar projection. But that doesn't necessarily mean that the vector B itself is the magnitude is greater or less, we're making it greater or less than its original magnitude. The magnitude does not change. But visually, we do sometimes extend it, such as here, or we extend it in the opposite direction here to see that scalar projection. But but it is independent of the length of B. And we can also say the other way. The projection of B onto A is independent of the length of the vector A. So again, we're going to use two different examples to show some properties of scalar projection. So starting with, we want to show algebraically that the scalar projection of A onto B is the same as the projection of A onto 2B. So this is what this claim here was, that the scalar projection is independent of the length of B. So the scalar projection of A onto B is the dot product A and B and divided by the magnitude of B. Now, the scalar projection of A onto 2B is the dot product of A and 2B and divided by the magnitude of 2B. But using the associative property with the scalar for dot products, this A dot product 2B is just 2 dot product of A and B. And similarly, from properties of scalars, when we are finding this magnitude here, we can factor out this 2, and this is 2 times the magnitude of B. So now rewriting this projection of A onto B, we have 2 in the numerator and 2 in the denominator, which cancel out, and this is that same value we were seeing up there. And these two projections are equal, so again, the projection of A onto B is independent of the length of B, as we just saw. Now, we also are asked to show algebraically that the projection of A onto B is not the same as the projection of A onto negative 2B. So this is now different because we have a negative here. So keep in mind here we used a property with 2 where we factored it out of this absolute value here. But when we are doing that, so we're following the similar process as above, but with that negative 2B, when we factor out the 2, it has now become a positive 2. So when you substitute it back into the projection of A onto negative 2B, then you have negative 2 in the numerator and 2 in the denominator. And so we actually end up with negative A dot product B in our numerator. So this is not the same projection that we saw above. So this will only hold for scalars that are positive values, not with the negative, because again, it's not necessarily the length that you are changing when you have negative, you're actually changing the direction of B. So it's one thing to say it's independent of the length of B, but it is not independent of the direction of B. So you can extend it, vector B in the same direction, so you can lengthen it or shorten it by any positive scalar, but once you have a negative scalar multiple, you're changing the direction. So this is a different procedure. So let's see now a worked example with numbers. So here we're given vector A, which is square root of 5, 3, 1, and vector B, which is 2 square root of 5, negative 1. And we're asked to find the scalar projection of A onto B and the scalar projection of B onto A. So first we find the dot product, which is going to be used in both scalar projections. So A dot product B, and remember now this is the dot product of algebraic vectors. So we multiply the x components plus the y components plus the z components. So then we end up with 5 square root of 5 minus 1. Now we also find the magnitude of both a and b. And so the magnitude of a is square root of 15. The magnitude of b is square root of 10. So the scalar projection of a onto b is the dot product over the magnitude of b. So this is just substitution from these values that we had up here. And we can rationalize this, or you can just input this into your calculator right away, and you will get 3.22. And the scalar projection of b onto a is that same dot product. So again, we have commutative property, so this is the same as a dot product b. And now divided by the magnitude of a, which was square root of 15. And so if you evaluate this one as well, you will get 2.63. So we can clearly see these two values are different. And so we don't have a commutative property with scalar projection. So the scalar projection of a onto b is different than b onto a. Now we are asked in this example to determine the angle that the vector OP given by 138 makes with each of the coordinate axes. So here, remember that the projection is independent of the length of the vector. So I will choose the 3 unit vectors, so I, j, and k, which correspond to the x-axis, y-axis, and the z-axis respectively. So then I'm going to define my 3 angles with each of those positive x-axes or positive axes. So we have alpha is the angle with the positive x-axis, beta is the angle with the y-axis, and gamma is the angle made with the z-axis. So now I'm just using that formula for finding the angle, which we saw last time. So for the x-axis, we have cosine of alpha is the dot product of OP and now the unit vector I on the x-axis. And now in the denominator, I have the magnitude of each of those. And same process with beta and gamma, but this time with beta, because it's the y-axis, we're using unit vector j, and with gamma, because it's the z-axis, we are using unit vector k. And also remember that the magnitude of I is equal to the magnitude of j, which is equal to the magnitude of k, and it is equal to 1. So now we find the dot product of OP with each of I, j, and k. And there actually is a pattern here because remember that I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. So when you find the dot product using the dot product for algebraic vectors, then really these two zeros are not contributing to our dot product. So really it's just whatever the x component is, which is times 1. So it's just the x component. And this is just the y component. And this is just the z component of OP as we saw up here, which was 138. So then we find also the magnitude of OP, which is just 1 squared plus 3 squared plus 8 squared, and the square root of that, which is square root of 74. And so substituting it back into our 3 expressions here now to find those angles. So alpha is the cosine inverse of the dot product, which was of OP and I, which was just 1. And the magnitude of OP stays the same for all of these. And remember, the magnitude of the unit vectors was just 1, so that's why it's not included here. So we have that square root of 74 in all of them. And we have that 138, which were the 3 dot products, as 138 here. And then finding the inverse cosine of each, we have 83.3 degrees, 69.6 degrees, and 21.6 degrees, which is the angle that OP makes with the positive x-axis, y-axis, and z-axis respectively. Now, we can generalize this now to call this, and this is called the direction cosines for any vector v, which is given by a, b, and c. So again, we have those 3 definitions of alpha, beta, and theta, which are going to be the angle angles made with the positive x, y, and z axis respectively. And so we can generalize this to cosine of beta is, or sorry, cosine of alpha is the dot product of the vector with just 1, 0, 0, which is just I, and this one is j, and this one is k. And in our denominator, we have the magnitude of the vector b. And so, again, remember, this one will just give you a over magnitude of b. This one will give you b over the magnitude of b. And this one will be c over the magnitude of v, if we just want a more simplified and general answer, we can also use these. And so to find the angles, all you would have to do is just find the cosine inverse of, for example, a over magnitude of b. So now we've seen scalar projections of a vector onto another vector, and now we're going to consider a vector projection onto another vector. So this is actually a very similar process. So when we are finding the vector projection of vector A onto B, this is equal to the scalar projection of A onto B, but multiplied by the unit vector in the direction of B, which is really just the vector B divided by its magnitude, which gives it a unit vector. So we really only care about the direction, but not necessarily the magnitude. And so this was the scalar projection of A onto B, and now this is the unit vector in the direction of B. And if you multiply this, we have A dot product B times the vector B. Again, we need this because of the direction. And in the denominator, we have the magnitude of vector B squared. Now, using the magnitude property of the dot product, this being magnitude of b squared, this is also just b dot product b, but we have to have that vector b is not equal to 0, or else this would just be 0, and we can't have a 0 in the denominator. So now what that will look like, so consider here vector a and vector b, and it's given by OA and OB. And the angle between them is theta. So we already saw scalar projection of A onto B, which you draw the line that is perpendicular to OB from vector A. And this quantity here is the scalar projection, and it is a scalar value. So remember, it's the magnitude of A times the cosine of theta. But now the vector projection is the same process, but now this is a vector and it is in the same direction of B. And that's why we need that direction or the unit vector in the direction of B, because it's giving us what that direction will be, because it's now a vector. We don't need just magnitude, we need to have a direction as well. So let's do a worked example here. We are given the vector OA given by 4, 3, and vector OB given by 4, negative 1. And we want to find the vector projection of OA onto OB. So let ON be the scalar projection, and this is just a line segment, and it'll be a scalar. And ON as a vector is going to be the vector projection of OA on vector OB. So first we find the magnitude of vector OB, which is just 4 squared plus negative 1 squared, and it's square root of 17. And now, again, I'm just finding all the values that I need at the beginning, and then I go back to substitute it into my formulas for scalar projection and vector projection. So here I also find the dot product between OA and OB, which is just the x components multiply plus the y components multiply, which gives me 13. So the scalar projection of OA on OB is their dot product, 13, over the magnitude of OB, which is just square root of 17, and ON is equal to 13 over 17. Now we find the unit vector, which is OB, vector OB divided by its magnitude. So vector OB was 4, negative 1, and we have to keep it as the vector here. And we're just dividing it by square root of 17, which will give me an And actually, I'm just leaving it like that for now. And then I'm going to substitute this whole value into my vector projection of OA onto OB, which is given by vector ON. And this is ON, which was the scalar projection. And this one is the, um, yeah, unit vector in direction of OB. And so the reason I did that is now because that square root of 17 times square root of 17 is just 17. And then I had that 13 in the numerator. So instead of distributing my scalar twice into the coordinates, I end up with my final scalar, which is 13 over 17. And then I distribute this. So then vector ON is given by 52 over 17 and negative 13 over 17. And let's look at it below here. This is vector OA, which is given by the point A43. And this is vector vector OB, which is given by the point B, and it's 4, negative 1. And now this is the line drawn from A onto B, which is perpendicular to vector B. And this is now that vector ON. So what we had to do was first find what the magnitude of ON is, and then use that to find now this vector. And now ON can be defined by its endpoints. So n being 52 over 17 and negative 13 over 17. And we have found our vector projection of OA onto OB. Now, we're taking a break from projections. We're going to look at our second application of dot product, which is work. So work is when a force is acting on an object and it moves the object from one point to another, we say that the force has done work. So the product of the distance of displacement of an object, so how much it has moved, and the component of the force along the line of the displacement is going to give us work. And I want you to think, based on these two values here, how do you think work connects to the dot product? So to give you a formula now for work, work is given by vector F taking the dot product with vector S. And vector F is the force acting on an object, and it's in newtons. And vector S is the displacement of the object, and with respect to the direction. So have we moved right, left, up, down, east, west? Where? Where have we moved? And so W, which is N times M, is the work done, and it is measured in a new unit, which is joules. And again, because work is F dot product S, this is a scalar value. And going back to our definition of dot product, this is the same as the magnitude of F times the magnitude of S times cosine of theta, where theta is the angle between the force and the displacement. So consider this example where he is pushing this box and the box is moving this displacement. So it has moved this amount of distance to the right and it ends up here. And the force that he's putting on it is both right and upward based on, for example, his placement on the box. And so this is the direction of the force vector, which is the force that he's putting onto the box. And so the work that he's done is going to be the dot product of F and S. So here I've given you an example. So Miss Genji is pulling her dog in a wagon and is exerting a force of 50 newtons, acting at 27 degrees to the ground. If Miss Genji pulls her dog a distance of 100 meters, how much work was done? So consider this diagram below. And guys, this is actually my dog, what my dog looks like. So I'm pulling her in a wagon and I have a force of 50 newtons. And so my horizontal component is pulling this wagon to the right, and the vertical component is moving it upward. But together, that combined force is just moving this wagon forward. And so from the diagram, we find that the magnitude of H, which is given by 50 cosine of 27 degrees, is 44.55. And the amount of work that I've done is the displacement, which was, I moved my dog a distance of 100 meters, and the work that I did in the horizontal direction here. So I'm only looking at that 44.55 N. And so this multiplied gives me 4,455 joules. So the work done by me is 4,455 joules, which again was the dot product that I got from here. And this was I already incorporated the cosine here when I found the horizontal component, and that's why here it's just a multiplication. Now, another application of the dot product is also power. So power measures the rate at which work is done by a force acting on an object in motion. So this is the product of the force vector and the velocity vector. And again, how do you think power connects to the dot product? So just to give you a definition, power is going to be the dot product of the force and velocity, where force is the force acting on an object in newtons, and v is the velocity of the object in motion. And it's measured in meters per second, and it has a direction, so it's a vector. And theta is the angle between the two vectors. And now P, which is the power, is measured in watt, which is shown by W. So if the force acts in the same direction as the motion, we say the power is positive. So it's making it move even more. If the force is perpendicular to the motion, this is just property of dot product, power is 0. And if the force opposes motion, then power is negative. So here, a tow truck is pulling a broken down car along a highway. The truck applies a force of 450 newtons at an angle of 30 degrees above the direction of motion. The car moves forward at a velocity of 20 meters per second. So here, power is the dot product of the force and velocity. So here is my magnitude of force, which was 450 newtons. Here's my velocity, which is a magnitude of 20. And then here's my angle, cosine of 30 degrees. And altogether, if you evaluate this, you get that power is about 7,794 watts. Or, remember, this is just conversion of units. So 1,000 watts is equal to 1 kilowatt. So then I can also say that this is approximately 7.8 kilowatts of power. And that was the last example and a wrap up of our applications of the dot product. So as you can see, it is really useful and it does have a lot of applications. And even projection itself has a lot of applications in real life. So please read more about it if you're interested and just if you're curious why dot product is useful for us. And please complete the practice questions below, as well as any additional work posted on Google Classroom. And don't hesitate to reach out if you have any questions. And I will see you all next class.